Here are the notes for Unit 3.6, Electric Potential. We've seen how the potential energy of a point charge in an electric field depends on the charge and the field and the distance. So just to go back and review this last example from the last section, we had a charge in an electric field, and we can change the potential energy of that charge by moving it in the field. In this case, if the positive charge moves toward the negative plate, it's going to lose potential energy, just like a ball dropping from the ceiling to the floor loses potential energy. Now what we'd like to do, though, is think about the concept of electric potential energy per unit charge. And I should write this the way that the College Board does. They write a U for potential energy. So this is called electric potential. Again, electric potential energy divided by the charge. And the unit for this is joules per coulomb, and a joule per coulomb is called a volt, named after Alessandro Volta, the scientist that did a lot of work with electricity at the turn of the last century. So it is the electric potential energy associated with a charged particle divided by the charge of the particle. And if we look at the change in electric potential, that's called potential difference. Now again, going back to our example, in many situations, we're looking at a difference. We're looking at what happens when we move the object from one point to another point. So we'd be looking at potential difference. Let's look and see what happens when we combine this equation with electric potential energy equals negative QED to form the following equation for a uniform field. Voltage, delta V, so this would be change in potential. This is also called potential difference. Equals negative E times D, where E is the electric field and D is the distance we move the charge. If we're working with point charges, what happens is we can take our equation for the electric field and we multiply it by a distance, and what happens is one of the r's cancels out and we end up with KQ over R. So we've got two different equations for potential difference. One is for a uniform field, and one is for a field created by a point charge. Let's revisit some examples. Example 1, in a uniform electric field. Find the electric potential possessed by an electron, located at the high potential plate if E is 30 newtons per coulomb and D is 20 centimeters. So in this scenario, what we've got is we know the magnitude of the electric field. It's 30 newtons per coulomb, and it's pointed downward. That's why I've got the negative there. And the distance between the plates is 0.2 meters. And so to find the potential difference, all I have to do is multiply E times D, and I get 6 Newton meters per coulomb, and a Newton meter is a joule, so this would be 6 joules per coulomb. Again, please remember that the positively charged plate is always the higher potential, and the negatively charged plate is always the low potential. So if we travel, or if the charged particle travels from the top to the bottom, it's losing potential, or there's going to be a negative change in potential. Let's look at how this works with gravity. Find the gravitational potential, I didn't proofread very well here, possessed by a 1 kilogram mass at the ceiling if G is 10 newtons per kilogram and D is 3 meters. So this is the same idea. We're going to take the strength of the field times the distance. The strength of the field is 10 newtons per kilogram. Actually, I should put a negative there because it's pointed downward. Times 3 meters. Now, 3 meters is also downward. And we would end up with, actually, there should be a negative on the equation itself. Let me rewrite this. The equation is negative GH. So I would plug in negative 10 and negative 3, and I would end up actually with an answer of negative 30 newton meters per kilogram, or an answer of negative 30 joules per kilogram. What this means is if I take an object and I change its position, so if it's at the ceiling and I let it fall to the floor, what's going to happen is that object is going to lose 30 joules of energy per kilogram of mass. So what's neat about this is I don't need to know the exact amount of mass. I have a ratio. I have an amount of energy per unit mass that's lost. The reason this is going to be useful is that later we're going to have different amounts of charges, different amounts of charge traveling, and we want to know how much energy is carried per unit charge. Let's look at some examples for electric potential for point charges. Find the electric potential at a distance of 1 centimeter away from a 5 coulomb charge. So here's the formula for electric potential around a point charge. K is still 9 times 10 to the 9th. Q is the charge, it's 5 coulombs. And the distance, 1 centimeter, I need to change to meters. And when I calculate that, I get 4.5 times 10 to the 12th, and the unit is volts. If I were to repeat this for a negative 5 coulomb charge, I would get the opposite value. And the reason for that is that when I plug in my numbers, I'm going to plug in negative 5 for Q. So I'll get the same value, but it will have a negative sign. Okay, next I'm going to introduce a concept called equipotential, or lines of equipotential. And I'm going to start again with a gravitational analogy. I don't know how many of you have seen this place in Wyoming, Devil's Tower, Wyoming. But Devil's Tower, Wyoming is it's a really cool geographical feature. It sticks up out of the ground, and if we look at Devil's Tower, obviously it sticks up out of the ground. But if we want to show on a two-dimensional map what the contour is of Devil's Tower, we use something called a contour map. This is a little bit fuzzy, but we'll try to illuminate this. So this line that I just drew is at 5,100 feet. That's the elevation. And you can see right at the very top of Devil's Tower is a point that actually measures 5117, so it's 17 feet higher at the very center. Then, just a little ways away, if I follow this line, that height is 5,000 feet. And you can follow the lines of equal gravitational potential energy, right? So anything that falls on this 5,000 foot line has a gravitational potential energy equal to mgh. And we would say that this is equipotential because the potential is the same at all points on this line. Now, remember that gravitational potential energy is mgh. Potential would just be GH. So it's just the strength of the field times the height. So now let's think about the gravitational field. If I were going to draw lines of equipotential, they would look like this. These purple lines that I'm drawing are parallel, and and any object that's somewhere on this line has the same potential. If I wanted to draw a line of equipotential around the Earth, it would be a circle. I can draw multiple lines of equipotential around the Earth, like that. Or if I'm kind of in between the surface and zoomed out, a line of equipotential would look something like that. Could probably do a little better. Let's see if I can do a little better. I didn't do any better. This is supposed to be equally distant from the surface of the Earth. So with point charges, I can do the same thing. I can make sort of a topographic map. So I want you to consider in a situation where we have a positive point charge and a negative point charge. Here, the lines of equipotential are drawn. So I'll just go over one in red here. So that is a line of equipotential. Remember that potential is V for voltage, and it's KQ over R. So the reason that there's a couple of reasons, but the reason that that's this equipotential is because R is the same. The radius of that circle is the same. And so that circle has the same voltage all the way around. I could do the same thing over here on the negative one. I would get negative values if I plugged into this formula. So the potential on the right side is positive and the potential on the left side is negative. Now, if I were going to represent that with a topographic map, it would look like this. The positive potential sort of pokes up, and the negative, so up here, and the negative potential is like a well. This is different than gravity. Gravity only goes in one direction. It's an attractive force. But electric potential can be positive or negative, and that's what we're trying to represent here. So here's another picture of a scenario with equipotential lines. Here are two negatively charged objects, and they've drawn the equipotential lines around them. And that's what it looks like. Finally, for a uniform field, the equipotential lines are parallel to the plates. They're perpendicular to the electric field. And the field works on a gradient. So if we've got 100 volts on one plate and 0 volts on the other plate, then right in the middle is 50 volts. Right in the middle is 50 volts. And right between 50 and 100 is 75. Right between 0 and 50 is 25. So let's look at this question. Which points shown below fall on the same equipotential? So the answer would be B and C would fall on the same equipotential because they are equidistant between the charged plates. Okay, this is a good time to introduce a new unit for work. Another unit for work is called the electron volt. So if we just go back, let's see. Oh, sorry. Okay. If I go back and I look at voltage, and that a volt is a joule per coulomb, what would happen if I take a joule per coulomb and I multiply it by charge? I'm going to get an amount of energy. Let me find my spot here. So a volt is a joule per coulomb. Now an electron volt, is the charge on an electron times a volt. So the charge on one electron would be 1.6 times 10 to the negative 19th coulombs, and then times 1 volt would be times 1 joule per coulomb. So when I multiply this out, I get that an electron volt is negative 1.6 times 10 to the negative 19th joules. This is the energy it takes to move an electron through 1 volt of potential. So here I would have 2 charged plates. I know that the left plate is negative because the potential is lower. I know that the right plate is positive because the potential is higher. And I'm going to move an electron through 1 volt of potential difference. And if I do that, the amount of energy that I would lose, or that the electron would lose, rather, is negative 1.6 times 10 to the negative 19th joules. Now, another way to say that is just to simply call that an electron volt. It's the charge on one electron, again, the charge on one electron times a volt. So if you see that unit, know that the electron volt is a unit of work, and 1 electron volt is equal to negative 1.6 times 10 to the negative 19th joules. Okay, a couple more examples. Find the potential difference between a point infinitely far away and a point 1 centimeter from a proton. So I'm going to use the formula for potential, and I'm going to do it twice. Once for 1 centimeter away and once for infinitely far away. And when I do that, let's see, I need to actually calculate this. I'm going to take 9 times 10 to the 9th times 1.6 times 10 to the negative 19th divided by 0.01. And I'm going to get 1.44 times 10 to the negative 7th volts. Example 2, if 10 joules of work is required to move 2 coulombs of charge in uniform electric field, the potential difference present is equal to what? So potential difference is joules per coulomb, or work per unit charge, or you can also think of it as energy per unit charge, because we know that work and energy are equivalent. So I would simply take 10 joules divided by 2 coulombs, and I get 5 joules per coulomb, or 5 volts. Okay, we're going to wrap it up with, oh no, we're not quite going to wrap it up. We are going to wrap up this video with example 3. Okay, example 3. Find the electric potential at a point at the center of the following diagrams. Okay, so we've seen these diagrams before. We're going to use the formula for electric potential, and we're also going to remember that electric potential is not a vector. So electric potential, there's an electric potential coming from each one of these 4 charges. Now, the amount of electric potential coming from each one of these 4 charges is K, Q, over the distance, and the distance is A times the square root of 2 over 2. So I could write it like this, or I could simplify it and have, and write it like this. The square root of 2kq over a. Now what happens is I simply add all of the potentials together, but the positive and negative ones cancel. So the potential from the plus q is going to cancel the potential from the negative q, because the potential from the plus q is going to be positive square root of 2kq over a, and this one's going to be negative square root of 2kq over a. So those two things, again, cancel, and I'm left with the potentials from the other 2 charges, which are the same amount. They're this square root of 2kq over a. So then I have 2 of those, which leads me to my answer, 2 times the square root of 2kq over a. Finally, in this last example that we're going to cover in this video, the voltage created, or the potential created by one of these four charges would be kq over d times the square root of 2 over 2, which simplifies to 2kq over d times the square root of 2. And then I simplified it again. It's 2 times the square root of 2kq over d. But there's four of these, and again, they add not as vectors, but simply as numbers. So if I add four of these charges together, I'll get 8 times the square root of 2kq over d. All right, thanks for hanging in there with me, and we will